All right, class, let me go this way here. So I do have to be at a meeting. Right now, we are going to go over 4.2 via video, and then we'll go from there. So I'm going to go like this. I'm going to have the videos pre-set by ink, and we'll kind of go over it this way here. So 4.2, after you have done your 4.1 homework, hopefully that would be good there. But 4.2 starts with something called the mean value theorem. The mean value theorem, it's not very mean at all. But mean, we're talking about average, right? Average value of something. And so before we even get to the mean value theorem, what we're going to do is we're going to look at something called Rolle's theorem. So his name is spelled R-O-L-L-E apostrophe S. So Mr. Rolle was at the anybody wants to even do a presentation on him, he at first despised calculus. He's one of the members, actually was a clerk for the New England Mathematical Society and was staunchly opposed to calculus. And then eventually, after a few years, he changed his mind about calculus. And then as he studied it, I think he developed three theorems in regards to calculus here. But this one is called Rolle's theorem, named after him. And so it has these conditions. And if these conditions are met, then there's a conclusion that always is. So first condition is this, that f is a continuous function. S has to be a continuous function on a closed interval from a to b, which means when you draw this function, you cannot lift your pencil off your sheet of paper. You have to draw it from a to b directly. Then the other piece is that f is differentiable, which means we can take a derivative of this function. And the derivative doesn't have to be at the exact endpoints because that's not how derivatives work, right? Because we talked about limits before, right? So it has to be differentiable on an open interval from a to b. And the third condition here is that f of a and f of b, they have the same exact y values. So they start at the same spot, they end the same spot, but it can go way differently in between. All right, what's the conclusion that Rolle came up with? That there is a number. There's a number called c, so some kind of constant that is inside the interval of a to b, where it's all differentiable, and such that it has this condition. That the derivative exactly at c is going to be equal to 0. That's it. That is Rolle's theorem. Again, this is calculus just kind of barely getting on the scene. We just got notation for it. And because of it, a lot of people are trying to figure out how things work. And Mr. will figure out a few things here. That's kind of cool. Okay, we're going to go on to the next step. Boom. And I'm going to get to my little drawing tool again here as we go here. So let's jam. So how do we graph this? With some images that come to mind. And I'm just going to stop right there. Okay. So just a little graphic on this Rolle's theorem. So here it is, X and Y grid. I'm starting off in A. I'm ending in B. And notice that f of A and f of B, they share the same Y value. But also notice that there is a graph that's connecting those two. So it goes up, then comes down for a little bit, then reaches back up to B. Okay, question is this. Is there ever a time in this interval that the derivative at a certain x value called c is equal to 0? And that's what Rolle was trying to prove. And yes, there is. There is a value somewhere here that will equal 0. In fact, there's two values, so I actually have to differentiate here. I have to say C1 and C2. There it is. C1, C2. Whoa, hold on. We're getting ahead of me here. C1 and C2, there's actually two places where the derivative would be equal to 0. We go from there. All right, another little graph of Rolle's theorem looks like this right there. So notice it starts at 0, 0, ends somewhere on the x-axis. And if that's the case, you know both those points share a common y value. So somewhere in between, there's going to be at least one point called C in which the derivative is equal to 0. That's cool. There it is. Rolle's theorem implies there's the slope of the 2 points, and then there's also the instantaneous slope. And those guys match. Okay, what we're going to do now is let's do a problem involving this. I'm going to jump to this guy here. Jump to this and jump to that. Okay. So example number 1. Let's go with it here. We are going to, yeah, that's right. We're going to verify. Verify Rolle's Rolle's theorem. I can probably make this go a little faster, but I'm going to kind of keep it there here. So exercise 1. And you guys can pause the video, obviously, if you need to here. So we're going to verify. You can put that Rolle's theorem. We can say applies in this situation. It applies. Then find the number. All right, here's our function, f of x equals, I got x to the third minus x squared, I think, minus 6x plus 2. All right, we're going from 0 to 3. So there's our graph there. All right, so we've got to check to make sure that Rolle's theorem applies. So does it meet the conditions? Number 1, is it continuous? Is that f of x continuous? Yes, of course it is continuous. Reason for it is because it is a polynomial function. And remember, polynomial functions, parabolas, x to the third, those guys are always continuous. I can always draw curves. Or a graph of a line going up and down. Those are parabolas. So x to the second, x to the third, x to the fourth, x to the fifth, whenever you see that graph, that is continuous on the number line. Second of all, is f differentiable? Can we take a derivative of that particular function there? That's the next step. Yeah, polynomial functions. It's actually, that was a theorem in the book, is if you have a polynomial function, you can take a derivative of it. All right, and number 3. Does our beginning value match our end value? That's the question. So I'm going to do the work here. You guys check it here. If I put in a 0 into this function, I'm going to get out a 2. If I put in a 3 into this function, the question is, does it come out with a 2? Let's see. Thinking 3 times 3 times 3 is 27. I'm thinking x squared, so 3 squared is 9, so subtract 9. And then I'm thinking 3 times 6 is 18, plus 2, which makes 2. So yes, absolutely. The value at 0, the value at 3, they both equal 2, but more importantly, they're equal to each other. Okay, so if that's the case, let's take a derivative. What is the derivative of the function? All right, it is 3x squared minus 2x minus 6. That is the derivative. Okay, so now the question is this. Rolle's theorem says if it meets the conditions, there has to be a C value that the derivative is equal to 0. It must be true in here. So your job is to find it. Go for it. Can you find it? Let me just pop this into presentation mode here. And let's go with it here. So I have the derivative. I set this guy equal to 0. And according to Rolle's theorem, it's an existence theorem, which means it does exist. Just may be hard to find it, but it does exist. So I'm thinking factoring. Anybody tried factoring on this guy? Does it factor? After a little while, usually students say, nope, doesn't factor. Okay, so then we're going to do is do the other way here. We're going to have to do the quadratic formula. So negative b plus or minus the square root of that same number squared minus 2, minus 4. Yeah, 4 minus 4 times a times c all over 2 times a. All right, copying that down. If you can stay ahead of me, that's even better. All right, let's go with it. I'm going to finish it up here. So let's see. That's going to be 2 on the outside. That's going to be 76 by the time it's done. It's 72. It's 72 plus 4, or 4 plus 72 is 76, all over 6. Now the question is this. Is that a perfect square? Does it break down any more at least? So because it's an even number, I know 2 will go into it. Or maybe even 3 will go into it here. Let's see. Yeah, 2. 2 goes into that 38 times. And then 38 is also a even number. So I know 2 will go into it in 19. Okay, if that's the case, I get doubles of 2. So 2 is the perfect square. 19 just stays there. So how about 2 plus or minus? 2 gets to go on the outside. 19 has to stay divided by 6. And if that's the case, let's reduce. Let's reduce this 2, that 2, and that 6 at the same time. So what's the number that goes into 2? 2 and 6. Obviously, it's 2. So if you divide 2 by 2, and then divide 2 by 2 again, leaves us with square root of 19, and then divide 6 divided by 2 makes us a 3. Okay, so now the question is this. I got 2 answers. Is there one of them? Well, actually, no. It could be the fact that it may be not even part of our domain. That's the issue. So notice that 1 minus, if you did a minus square root of 19, divided by 3, that definitely would give you a negative number. So we're not interested in that. On your calculators, check this for me. I'll plug in 1 plus the square root of 19. Divide all that by 3. And just to check, make sure that that number is between 0 and 3. And sure enough, it is. Okay, that's the case. We found our C value. Our C value is 1 plus or minus. I'm sorry, no more minuses here. It's 1 plus square root of 19 over 3. Done. There it is. There's our final answer. So there's an existence. Yep. And just we found what that particular number is. In mathematics, it is interestingly enough, there's multiple times where you actually we know that something exists, but we cannot find that something. It's just the strangest thing, just like in this case. We have a lot of those sort of questions in mathematics. All right, but moving on. So now let's move on to actually what is called the mean value theorem, which is the topic here. So we'll go through defining it, and then we'll go through one example with it as well. So let's go with it. The mean value theorem. So it should be all right, it should be a modification of Rolle's theorem. So let's see how this is modified. So first things first, f has to satisfy the following conditions. Number one, f is continuous from A to B. Hey, that's very similar to rules, right? It has to be continuous. You have to be able to graph from A to B without lifting off your pencil off your sheet of paper. Next, f is differentiable on A to B. Absolutely. Can't find where the derivative equals 0 when you can't even take the derivative of it. So yeah, there it is. That's a cause. And then if those conditions are met, then we have this. Let me graph it for you. See if this makes sense right there. So notice we took off condition number 3. Now we're saying a little more generally, who cares what the y value is? I know that between any two y values, I can calculate the slope there. That's algebra. But it says that I can find a value somewhere during this process in which the slope is the same as the value itself. So here it is, I will write it. The derivative at some c value is going to be equal to the slope between a and b. So basically an average slope is going to be equal to an instantaneous slope sometime during this process, at least once. All right, so let's do an example. Example 2. So verify that this fulfills the mean value theorem, and then find c. So function x to the third plus x minus 1, and we're going to go from 0 to 2. All right, so first things first, is this continuous? Yes, polynomial functions are continuous. That's the way they are. From negative infinity to positive infinity, so definitely between 0 and 2. Number 2. All right, is it differentiable? Absolutely, polynomial functions are differentiable. Okay, so then let's find this right here. Let's find the derivative. The derivative of 3x squared plus 1. And let's find this right here. Let's go with the slope between the 2 points here. So if you plug in a 2 into the function itself, that's what this is right over here. Plugging in a 2, this is minus f of 0, and then it's 2 minus 0. So plug 2 into this little function gives us a 9. That's going to be let's see, it's going to be, 8 plus 2 minus 1. If I plug in a 0, I'm going to actually get a negative 1 out of this. And it'll be 2 minus 0 on the bottom. Subtracting a negative, same thing as adding a positive. So it'll be 10. 10 divided by 2 is a 9, and done. Actually, no, not done. It's 5. 10 divided by 2 is 5. Okay, so now what do we know? We know that sometime during this process, the instantaneous slope is going to be 5. So let's jam with it. Let's put our derivative, 3x squared plus 1, is equal to 5. So yep, there it is. Let's solve this guy. So notice you don't have a linear form of x. You just have quadratic form. So you can do quadratic if you like. You'll be just fine. You could also just solve it. This is something called solving the square root method of solving an equation. If you guys remember, that's the square root method of solving an equation. Here we go. Divide by 3, divide by 3. And so notice we have the perfect square trinomial all by itself on one side. How do we get rid of it? What we do is we take the square root on both sides. Square root over here, square root over here. Don't forget plus or minus. All right, if that's the case, then the 4 becomes a perfect square of 2. The 2 goes out. 3 still stays. Then it wants to get all the rational numbers on top. So we're going to multiply both sides by root 3. And we get ourselves plus or minus 2 root 3 over 2. Okay, now real quick here. Test on your calculator. Obviously, the negative is not going to work. It's a negative number, but is 2 times root 3 divided by 3. Is that a number between 0 and 2? Check on the calculators, and that is true. So yes, we found our number, not the negative one, but the other one. So we should probably write it as C. Let me see if I can write this. So C is equal to up to root 3 over 3. There it is. There's our final answer. All right. And hopefully that helped.